The encryption protecting your enterprise data will become obsolete. This isn't hypothetical, and it isn't a distant future problem. It's already happening, because adversaries are harvesting your encrypted traffic today to decrypt it when quantum computers arrive. And the single factor that determines whether your organization survives that transition isn't which algorithm you pick. It's whether your infrastructure can change algorithms without breaking. And that's the part most organizations aren't ready for. Because the threat isn't what you think it is. It's not a future computer breaking your encryption. It's a present-day theft, data being stolen now, decrypted later. And the fix isn't just a new algorithm. It's a structural change to how your infrastructure handles cryptography. The algorithms exist. NIST has standardized them. Microsoft is shipping them. Browsers are enabling them by default. The technology is moving. What isn't moving fast enough is the architecture underneath it. Because most enterprises have cryptography that's hard-coded, undocumented, and scattered across systems that nobody's audited in years. When an algorithm needs to change, the change can't propagate fast enough to matter. So let's walk through the entire picture. The threat, the replacement algorithms, the performance costs, the hidden dependencies in your infrastructure, the architectural shift that makes the transition survivable, and what's already available in the Microsoft stack today. And by the end, the question won't be whether you need to migrate to post-quantum cryptography. The question will be whether your infrastructure is built to handle any algorithm transition, not just this one. The harvest now problem. So let's start with what's actually happening right now, because the threat isn't theoretical and it isn't waiting for a quantum computer to exist. It's called harvest now, decrypt later. And the mechanism is straightforward. An adversary intercepts your encrypted network traffic, whether that's TLS sessions connecting your users to Microsoft 365, VPN tunnels running between branch offices and headquarters, SSH sessions used for remote server administration, or API calls from Power Automate connectors to external services. They can't decrypt any of it today because the encryption works. RSA and ECC are still hard to break on classical computers. The mathematical problems they rely on, factoring large integers and solving discrete logarithms, remain computationally infeasible at the key sizes we use. But they don't need to decrypt it today. They store it. They hold onto it for years, sometimes a decade or more, waiting for the day when a quantum computer can run Shor's algorithm against the key exchange that protected those sessions. Once that happens, every captured session key gets derived retroactively, and all the data that was supposed to stay confidential for 10 or 20 years is suddenly exposed. Health records, trade secrets, classified information, intellectual property with multi-decade value, legal documents covered by attorney-client privilege, financial histories that regulators require you to retain, all of it becomes readable by the adversary who had the patience to wait. And to understand why this is credible, you need to understand the basic mechanics of quantum computing and where the technology actually stands. Quantum computing derives its power from the physics of qubits, quantum bits that can occupy superpositions of states and exhibit entanglement. In classical computing, bits are strictly 0 or 1. And algorithms operate by sequentially evaluating discrete states. A 64-bit register can represent 1 out of 2 to the 64th power possibilities at any instant, and a classical algorithm must effectively traverse or sample that space step by step. In contrast, a small register of qubits can encode a superposition over many possible states at once, and appropriately designed quantum algorithms can use interference to amplify amplitudes of correct answers while canceling incorrect ones, achieving speedups on specific problem classes. This doesn't mean quantum computers are universally faster than classical machines. Their advantage is problem-dependent and typically arises when the structure of the problem allows a quantum algorithm to exploit superposition and entanglement to reduce complexity from exponential to polynomial time. Quantum computers aren't expected to replace classical computers, but to coexist as specialized accelerators, accessed through cloud platforms and APIs in much the same way that organizations consume GPU-accelerated AI services today. But for security professionals, the relevant point is that public key cryptography relies on mathematical problems that are known to be efficiently solvable on a sufficiently large, fault-tolerant quantum computer using Shor's algorithm. And the distinction between physical qubits and logical qubits matters for understanding the timeline. Physical qubits are the noisy, error-prone hardware units. Logical qubits are the error-corrected, reliable computational units built from many physical qubits. Current quantum processors have hundreds to thousands of physical qubits, but the error rates are high enough that logical qubits are scarce. IBM's Nighthawk processor, announced for 2026, operates 120 logical qubits, which is a significant milestone but still far below the roughly 2,330 to 4,099 logical qubits estimated to be necessary to break P256 or RSA 248. Palo Alto Networks characterizes harvest now, decrypt later as the most immediate quantum-related danger because it exploits vulnerabilities that exist right now in your key exchange and long-term storage. The encryption itself isn't broken yet, but the confidentiality of the data is already on a timer, and that timer is shorter than most enterprise planners assume. The Global Risk Institute published their 2025 Quantum Threat Timeline report, surveying 26 experts in the field. The respondents estimated a 28 to 49% probability that a cryptographically relevant quantum computer would exist within 10 years. For the 15-year horizon, the probability jumped to 51 to 70%. That survey reflects expert judgment rather than physical proof, but it's worth noting that a substantial fraction of specialists view a sub-15-year timeline as likely rather than speculative. And the overall conclusion was that the threat timeline has accelerated relative to prior years. Industry roadmaps reinforced that acceleration from different angles. IBM announced it's on track to demonstrate verified quantum advantage by the end of 2026 using its Nighthawk processor. Google's quantum AI roadmap aspires to a useful, error-corrected quantum computer by 2029, building on its 2019 quantum supremacy experiment. Google also accelerated its post-quantum cryptography migration timeline in April 2026, signaling that the company views the risk window as compressing. Quantinuum's roadmap sets a target of universal, fault-tolerant quantum computing by 2030. Pascal's neutral atom roadmap aims at 10,000 qubit devices by 2027, oriented toward optimization and simulation rather than specifically cryptanalytic workloads. IonQ has reported quantum advantage results on specific problem classes. The milestones vary, and none of them claim a precise date for breaking RSA, but the direction is consistent. Now, some vendors have put more aggressive stakes in the ground. Post-Quantum, a quantum-safe vendor, published an analysis arguing that 2030 is a plausible year for RSA 2048 to be broken by a sufficiently advanced quantum computer. That claim isn't universally endorsed and should be treated as a scenario from a motivated vendor rather than an accepted prediction. Security vendors like Palo Alto Networks frame Q-Day as likely arriving in the 2030s, citing forecasts from Forrester and Google Quantum AI, and noting that advances in logical qubit error correction have shortened earlier 2035 estimates, although these remain projections rather than empirically confirmed dates. And then there's the regulatory pressure, which is arguably the most concrete signal available because governments don't set mandatory transition timelines for hypothetical threats. The European Union's post-quantum roadmap directs member states to begin transitioning to post-quantum cryptography by the end of 2026, with critical infrastructure to be transitioned no later than 2030 and full transition by 2035. The US CNSA 2.0 timeline, issued by the NSA, sets specific milestones. 2025 for new software and firmware signatures, as well as web browsers, servers, and cloud services adopting CNSA 2.0 algorithms. 2026 for traditional networking equipment, including VPNs and routers. 2027 and beyond for operating systems and new national security systems. And 2035 for complete transition across all national security systems, with traditional asymmetric crypto not to be used beyond end of 2030 for relevant national security uses. Canada requires initial departmental migration plans starting April 2026, with annual reporting, high-risk systems complete by end of 2031, and remaining systems by 2035. Australia's ASD mandates that traditional asymmetric crypto must not be used beyond end of 2030 in certain contexts, with a refined transition plan due by end of 2026 and transition of critical systems beginning by end of 2028. The UK NCSC's phased approach calls for discover and plan around 2028, prioritize and pilot from 2028 to 2031, and complete adoption from 2031 to 2035, with strong emphasis on centrally managed, non-rushed migration and hybrid solutions. These timelines create external pressure on every cloud vendor, including Microsoft, to have mature PQC options available by the late 2020s, with pilot and early adopter capabilities in the mid-2020s, including right now in 2026. And the pressure is not just regulatory, it's also competitive. Organizations that can demonstrate PQC readiness to their customers, especially in regulated industries like finance, healthcare, and government contracting, have a market advantage. Organizations that can't demonstrate readiness face procurement disadvantage because customers with their own PQC compliance requirements will select vendors that can meet them. The migration to post-quantum cryptography is becoming a differentiator, not just a compliance checkbox. So the question for enterprise planners isn't really when will Q-Day arrive. The question is whether the math works out for your specific data. ISACA's quantum risk assessment guidance frames this as an inequality. X is the data retention period for a given asset, how long the data needs to stay confidential. U is the estimated migration time to get that asset protected by post-quantum cryptography. Z is the projected collapse time, when a quantum computer can break the encryption. When X plus Y exceeds Z, the asset is at risk under a harvest now decrypt later scenario and should be prioritized. Because many enterprises retain highly sensitive data for 10 to 20 years or more, and because large-scale cryptographic migrations can themselves take many years, the prudent stance is to assume that some data being protected today will still need to remain confidential when quantum computers become cryptographically relevant. Insurers with long-tail claims histories that stretch back decades, healthcare providers with lifetime medical records, manufacturers with long-term intellectual property that underpins revenue streams for product cycles lasting 15 years. Financial institutions with regulatory retention requirements spanning 7 to 25 years depending on the record type, government agencies with classified information that must remain secret for 30 years or more. All of these organizations face the inequality right now, even though the quantum computer doesn't exist yet. Now, symmetric cryptography faces a different quantum threat that's worth understanding. Grover's algorithm provides a quadratic speedup for searching an unstructured space, which translates into halving the effective security level of symmetric ciphers. A 128-bit AES key would offer roughly 64 bits of quantum security, which is insufficient. A 256-bit AES key would still offer approximately 128 bits of quantum security, which still holds up against quantum attacks. Security guidance from vendors including Palo Alto Networks and Fortinet recommends favoring AES 256 and stronger hash functions like SHA-384 or SHA-512 over weaker 128-bit keys and deprecated hashes like MD5 or SHA-1 as part of quantum readiness. But the main systemic shock arises from the breakage of asymmetric primitives used for key exchange and digital signatures, because those are what establish the secure channels and verify identities across every layer of your infrastructure. Symmetric algorithms are less vulnerable, but the protocols that negotiate the symmetric keys depend on asymmetric algorithms that are. But there's a counter-argument worth acknowledging because it's not wrong and it brings important nuance. A discussion hosted by the ISC2 security community contends that harvest now decrypt later attacks are only efficient for highly targeted, high-value intelligence campaigns, capturing and storing vast amounts of encrypted traffic for a decade or more, and then breaking thousands or millions of key exchanges is extremely costly and uncertain. The storage alone is non-trivial, and the compute required to break each key exchange individually would be significant even with a capable quantum computer. That analysis suggests that losing confidentiality of most enterprise data 10 to 15 years in the future would rarely cause operational damage, and that for many organizations, real-time threats like harvest now decrypt now attacks, which exploit cryptographic technical debt and weak protocols that are already breakable today, are more pressing. Both perspectives can be reconciled in a risk-based framework. For enterprises holding data whose compromise in 10 to 20 years would still be highly damaging, harvest now, decrypt later is a material risk that should influence near-term post-quantum priorities. For other data, the more relevant risks are second order. The collapse of PKI undermining software updates and identity systems, the need to replace vulnerable algorithms rapidly in response to new cryptanalytic results, and the challenge of doing so without destabilizing business operations. Q-Secure, a quantum-safe vendor, frames a key business question as the value horizon of sensitive data. If information will remain valuable beyond about 2030, then organizations should begin implementing quantum-safe protections now, because data stolen before migration can't be retroactively protected. In this view, trade secrets with multi-decade value, long-lived personal data subject to regulatory protection, classified information, and intellectual property underpinning future revenue streams are particularly attractive targets for harvest now decrypt later campaigns, justifying immediate action to deploy PQC, at least for high-value assets. IBM and other vendors echo this logic in their warning that any TLS data snooped and stored today could be decrypted in the future when quantum computers can run Shor's algorithm against the classical key exchange mechanisms. The risk isn't theoretical. It's a consequence of the mathematical fact that RSA and ECC key exchange can be broken by a sufficiently large quantum computer, combined with the practical fact that encrypted data can be stored indefinitely at low cost. And that last point is the one that matters most for this conversation. Because in all cases, focusing solely on harvest now decrypt later obscures the broader lesson. Quantum computing merely accelerates the need for cryptographic agility that's already apparent from past algorithm deprecations and protocol shifts. Think about the deprecation of SHA-1, which was deprecated in 2017, and organizations are still cleaning up SHA-1 dependencies in 2026. The forced migration from TLS 1.0 and 1.1, which were deprecated in 2021, and legacy systems still running those protocols are still being discovered in enterprise networks. the ongoing retirement of 3DS. None of those were quantum related. All of them caused years of painful, expensive remediation because infrastructure was rigid and couldn't adapt quickly. The quantum threat makes the next deprecation existential rather than inconvenient, but the structural problem is the same. The real problem isn't that a future computer will break your encryption. The real problem is that when that happens, or when the next algorithm gets deprecated, or when the next compliance mandate drops, your infrastructure probably can't adapt fast enough. And that's the shift in framing that matters. Most conversations about quantum risk focus on the timeline. When will the quantum computer arrive? But the timeline is uncertain. What's certain is that your infrastructure is rigid, and that rigidity is what turns a manageable algorithm transition into an existential crisis. Whether Q-Day arrives in 2030 or 2040 or 2050, your organization will face algorithm transitions between now and then. Deprecations happen, protocols get retired, compliance requirements change. The quantum transition is the one with the highest stakes. But it's not the only one your infrastructure will face. And there's something else worth knowing before we go further. Most organizations are already partially protected against this threat, and they don't even realize it. We'll come back to that. The new math. So the data is being stolen now. But here's what makes this different from every other security threat you've dealt with. The fix isn't a patch, and it isn't a configuration change. It's a mathematical shift. The public key cryptography that protects your entire digital infrastructure relies on two mathematical problems: integer factorization, which is the basis of RSA, and discrete logarithms over finite fields or elliptic curves, which underpin Diffie-Hellman and ECC. These problems are believed to be hard for classical computers, meaning no efficient algorithm is known to solve them at the key sizes we use today. RSA 2048, RSA 3072, P256, P384, all of these are secure against classical attacks because the best known algorithms for factoring and discrete logarithms require exponential time relative to the key size. But Shor's algorithm changes the equation entirely. Once a quantum computer can reliably control enough logical qubits with sufficiently low error rates, factoring large integers and solving discrete logarithms can be performed in polynomial time. The hardness assumptions that RSA and ECC depend on collapse. And because these algorithms underpin TLS, VPNs, SSH, software updates, code signing, and the entire PKI-based identity and access infrastructure, the arrival of a cryptographically relevant quantum computer would cause a systemic collapse of existing public key infrastructure if defenses aren't in place. This is worth emphasizing because it's not just one protocol or one service that breaks, it's the entire trust model that modern computing is built on. Your TLS connections break, which means your web traffic, your API calls, your SaaS access, your cloud management interfaces are all exposed. Your VPN tunnels break, which means your remote access and site-to-site connectivity are compromised. Your SSH sessions break, which means your server administration is exposed. Your code signing breaks, which means the integrity of your software updates can no longer be verified. Your certificate infrastructure breaks, which means identity verification at every layer fails. The problem isn't isolated to any single system. It's systemic because asymmetric cryptography is the foundation that everything else builds on. So the question becomes, what replaces the broken algorithms? In 2016, NIST launched an open international process to evaluate and standardize new post-quantum cryptographic algorithms. The core requirement was that candidate algorithms be based on mathematical problems believed to be hard for both classical and quantum computers, thereby avoiding the specific vulnerabilities exploited by Shor's algorithm and other known quantum techniques. The process ran through multiple rounds of evaluation, with submissions from cryptographers worldwide. In the first round, 69 candidate algorithms were evaluated. Many were broken in the early rounds, some within weeks of submission. The second round narrowed the field. The third round identified the finalists and alternates. This wasn't a quick process, and it wasn't supposed to be. The rigor of the evaluation was the entire point. In August 2022, NIST announced an initial selection of 4 algorithms: Crystal's Kyber for key encapsulation, Crystal's Dilithium and Falcon for digital signatures, and Sphinx Plus as a hash-based backup signature scheme. And in August 2024, the first 3 finalized Federal Information Processing Standards were released. FIPS 203 defines MLKM, a module lattice-based key encapsulation mechanism derived from Crystal's Kyber, intended to serve as the primary standard for general encryption, particularly for establishing shared symmetric keys over insecure networks. FIPS 204 defines MLDSA, a module lattice-based digital signature algorithm derived from Crystal's Dilithium, designed as the primary standard for digital signatures used in identity authentication, code signing, and certificate issuance. FIPS 205 defines SLH-DSA, a stateless hash-based digital signature algorithm derived from Sphinx Plus, which uses a fundamentally different mathematical approach as a backup in case lattice-based schemes are later found vulnerable. A fourth draft standard, FIPS 206, is planned around Falcon, which will be named FNDSA, and will offer another lattice-based signature option optimized for different performance and size trade-offs. As of June 2026, FNDSA has been submitted for draft approval but hasn't been finalized yet. Falcon produces smaller signatures than MLDSA at comparable security levels, which makes it attractive for bandwidth-constrained applications, but the implementation complexity is higher, and the verification process involves floating-point arithmetic that requires careful handling to avoid side-channel vulnerabilities. So the replacement algorithms exist, and they're built on a completely different mathematical foundation. RSA and ECC rely on number-theoretic problems in relatively low-dimensional spaces. You're factoring a single large integer, or solving a discrete logarithm over a curve. The math is elegant and well understood, but it has the specific algebraic structure that Shor's algorithm exploits. Quantum computers can use superposition and entanglement to efficiently navigate that structure, reducing what should take exponential time on a classical computer to polynomial time on a sufficiently large quantum computer. The new algorithms rely on problems in high-dimensional geometric structures called lattices. A lattice is a regular grid of points in a multidimensional space. You can think of it as a crystal structure in a space with hundreds or thousands of dimensions rather than the 3 dimensions we're used to. The security-relevant problem is finding the shortest vector in that space, the point closest to the origin. This is called the shortest vector problem, or SVP. In 2 or 3 dimensions, finding the shortest vector is easy. You can see it. In 1,000 dimensions, it becomes extraordinarily difficult because the search space grows exponentially with the number of dimensions, and there's no known technique, classical or quantum, that can efficiently navigate that space to find the shortest vector. The best-known algorithms for solving SVP in high dimensions still require exponential time, even with quantum assistance. The reason Shor's algorithm works against RSA and ECC is that factoring and discrete logarithms have exploitable algebraic structure. The problem can be decomposed into subproblems that a quantum computer can solve in parallel using the quantum Fourier transform. Lattice problems don't have that kind of decomposable structure. The shortest vector problem is a geometric search in a high-dimensional space, and there's no known quantum algorithm that can exploit the structure to find a speedup beyond what classical lattice reduction algorithms already achieve. That's the mathematical shift in one sentence. You're moving from problems with exploitable algebraic structure to problems that resist it. NIST emphasizes that these PQC algorithms are ready for immediate implementation and that organizations should begin migrating now, both because the timing of a cryptographically relevant quantum computer is uncertain and because modern infrastructures require many years to transition. The algorithms are designed to address 2 core tasks for which encryption is typically used: general encryption, covering key establishment and confidentiality of data in transit, and digital signatures, covering identity, integrity, and non-repudiation. Unlike RSA and ECC, which rely on integer factorization and discrete logarithms, the new algorithms use structured lattices and hash-based constructions that currently resist all known classical and quantum attacks, although ongoing cryptanalysis remains essential to validate their robustness over time. And that last point is worth pausing on. The phrase currently resist all known attacks is not the same as will resist all future attacks. Lattice cryptography is relatively young compared to RSA and ECC, which have been studied for decades. The possibility that a future cryptanalytic breakthrough could weaken lattice-based schemes is real, which is exactly why NIST standardized SLHDSA as a hash-based backup built on entirely different mathematics. And it's exactly why cryptographic agility matters more than any single algorithm choice. If you build your infrastructure to be agile, a future cryptanalytic result against lattices would trigger an algorithm rotation, not an infrastructure rebuild. And there's a practical implication of this shift that matters for the migration. Because the new algorithms use a different mathematical foundation, they require different implementation techniques. RSA and ECC rely on big integer arithmetic, which is well optimized in existing hardware and software. Lattice algorithms rely on polynomial arithmetic and number-theoretic transforms, which require different optimization strategies. This means that existing RSA and ECC hardware accelerators can't be reused for lattice operations. New hardware designs and standards are needed for FPGA, ASIC, and HSM implementations of post-quantum algorithms. The existing decades of engineering that went into optimizing RSA and ECC don't transfer to the new algorithms. This is a one-time cost of the transition, but it's a real one. Now, there's an important distinction within lattice cryptography between structured and unstructured lattices. MLChem and MLDSA use module lattices, which have a certain amount of algebraic structure that enables smaller keys and faster operations. This structure introduces slightly stronger assumptions than unstructured lattice schemes like FrodoChem, which relies on plain learning with errors and has larger keys, around 19 kilobytes for a key exchange at 128-bit security, compared to about 1.2 kilobytes for MLChem 768. The trade-off is between efficiency and conservative assumptions. NIST selected the structured schemes as primary standards because the efficiency gains are essential for practical deployment at internet scale, while also standardizing SLHDSA as a hash-based backup that relies on entirely different mathematics. Now, each of these algorithms serves a different role in your infrastructure, and understanding those roles is necessary for planning the transition. ML-CAM is a key encapsulation mechanism, meaning it's used to establish a shared secret between parties over an insecure channel. The workflow works like this. The client and server agree on public parameters. The server publishes an ML-KM public key. The client generates a random secret and encapsulates it using the public key to produce a ciphertext. The server decapsulates the ciphertext with its private key to recover the same secret. Both parties then derive a symmetric key using a key derivation function. This shared secret becomes the session key for symmetric encryption, typically AES. ML-KM replaces the RSA key transport and ECDH key agreement in your TLS handshakes, VPN negotiations, and SSH key exchanges. MLDSA is a digital signature algorithm used to sign messages so that any verifier with the public key can check authenticity and integrity. This is what replaces RSA signatures and ECDSA in your certificate chains, your code signing processes, your document signing workflows, your identity tokens, and your software update verification. When you enroll a certificate from a certificate authority, the CA signs it using its private key. When you sign a PowerShell script for execution policy, you're creating a digital signature. When Entra ID issues an access token, that token is signed. All of these signing operations will eventually use MLDSA instead of RSA or ECDSA. SLHDSA is the insurance policy. It's hash-based, not lattice-based, meaning it relies on an entirely different mathematical foundation. Hash-based signatures derive their security from the collision resistance and pre-image resistance of hash functions, which are not known to be vulnerable to quantum attacks beyond Grover's quadratic speedup. If someone discovers a quantum algorithm that breaks lattice problems, SLHDSA still stands. The trade-off is that SLHDSA signatures are significantly larger and slower than MLDSA, which is why it's positioned as a backup rather than the primary standard. SLHDSA signatures at the smallest parameter set are still around 8 kilobytes, compared to roughly 2.4 kilobytes for MLDSA 65. And that architectural choice, having a backup algorithm built on different math, is itself a form of cryptographic agility. NIST is already practicing what they're preaching. Don't bet everything on one mathematical assumption. Build redundancy at the algorithm layer so that a single cryptanalytic breakthrough doesn't collapse the entire system. But here's what most enterprises miss when they read about these new standards. These aren't drop-in replacements. The keys and ciphertexts for ML-CAM are measured in kilobytes, not hundreds of bytes. The signatures for MLDSA are 4 to 10 times larger than RSA signatures at comparable security levels. The math is different, the performance profile is different, and the infrastructure impact is different. And that's the part that turns a theoretical migration into an engineering problem, because the algorithm swap itself is straightforward at the mathematical level, but the deployment of larger keys and signatures across an infrastructure that was designed for small ones creates friction at every layer: the network layer, the protocol layer, the certificate layer, the hardware layer, and the application layer. Each layer can be addressed individually, but the coordination across all of them simultaneously is what makes the migration hard. The performance reality check, and this is where the post-quantum transition gets expensive, because the bottleneck isn't compute, it's bandwidth. Let's look at the numbers in detail because the specific sizes matter for planning. A standard X25519 elliptic curve key exchange, which is what most TLS connections use today, requires 64 bytes of communication between client and server. That's 32 bytes for the client's public key contribution and 32 bytes for the servers. It's tiny. It fits comfortably in a single TCP segment with room to spare for the rest of the client hello message. ML-KM 768, which is the NIST recommended replacement at a comparable security level, requires roughly 2,272 bytes for the same key exchange. That's about 37 times larger than X25519. The public key alone is around 1,084 bytes, compared to 32 bytes for X25519. The ciphertext is similar in size. On the CPU side, the story is actually positive. ML-CAM decapsulation is often faster than RSA private key operations, especially for the server side, which is where the computational burden typically lands. The lattice operations use polynomial multiplications and matrix vector products over small moduli, typically 11 to 13-bit primes, which are highly parallelizable and benefit from modern CPU features like SIMD instructions and number-theoretic transforms. Cloudflare has noted that lattice-based key exchange is often as fast and sometimes faster in terms of CPU time than elliptic curve operations. RSA private key operations are generally slower than either ECC or lattice CAMs at comparable security levels, especially on constrained devices without dedicated RSA hardware. But CPU speed doesn't matter when the handshake doesn't fit in a single network packet. TLS operates over TCP, and TCP has a maximum segment size determined by the path MTU, typically around 1,460 bytes on a standard Ethernet network. When the client hello message grows from a few hundred bytes to over 2 kilobytes, you hit fragmentation issues. The handshake splits across multiple TCP segments. Each additional segment requires another round trip on the network, and on high latency connections, that adds measurable delay. On lossy networks, each additional packet is another chance for a retransmission that could add hundreds of milliseconds to the handshake time. The Quake protocol, which underlies HTTP3, adds another dimension to this problem. QuICy runs over UDP and handles its own encryption and congestion control. Larger client, hello messages in Quix can cause the initial datagram to exceed the typical UDP MTU, forcing a fallback to a more expensive handshake flow that sends the initial message in multiple datagrams. This is one of the areas where the post-quantum transition creates protocol-level complexity that goes beyond simply swapping algorithm implementations. On middle boxes that inspect TLS traffic, larger handshakes can trigger bugs or timeout failures that were never tested with post-quantum cipher suites. Enterprise firewalls, intrusion detection systems, and TLS inspection appliances often have hard-coded expectations about the maximum size of TLS messages. When those expectations are violated, the middle box may drop the connection, reset it, or silently strip the unknown cipher suite from the client hello, forcing a fallback to classical-only key exchange and defeating the post-quantum protection entirely. This is not a theoretical failure mode. It's been observed in practice during early PQC TLS testing, and it's one of the reasons the migration requires careful canary testing before broad rollout. The canary testing approach matters for this audience because many organizations deploy TLS inspection appliances as part of their Microsoft 365 security architecture. These appliances intercept and inspect TLS traffic between users and M365 services, which means they sit in the path of every browser-to-cloud connection. If your TLS inspection appliance doesn't handle larger post-quantum handshakes correctly, it becomes a single point of failure for the PQC upgrade. And because these appliances are typically managed by a different team than the one managing the browser deployment, the coordination problem is real. And then there's the state management. A server terminating millions of TLS connections per day, think Azure front doors, Microsoft 365 load balancers, API gateways for Power Platform, has to maintain state for each handshake in progress. Larger handshake messages mean more memory per connection, more buffer management, and more pressure on the TLS state machine. At the scale of a major cloud provider, this compounds into real infrastructure cost, more RAM per server, more connection tracking capacity, more careful tuning of TCP parameters like the initial congestion window. Cloudflare has noted that accommodating lattice overhead in TLS involves dealing with TCP fragmentation and reworking the protocol stack in PKI to handle larger keys and messages. For signatures, the overhead is even more pronounced. An RSA 248 signature is 256 bytes. An RSA 3072 signature is 384 bytes. An MLDSA 65 signature at a comparable security level is roughly 2,120 bytes. An MLDSA 87 signature at a higher security level is about 4,195 bytes. That's a 4 to 10 times increase per signature depending on the security level you're comparing. Now think about what that means for certificate chains. An X509 certificate carries the public key and the signature from the issuing certificate authority. A typical TLS certificate chain today has 2 or 3 certificates: the end entity certificate, an intermediate CA certificate, and optionally a root CA certificate. With RSA 248 or ECDSA P256, each certificate is roughly 1 to 1.5 kilobytes, so the full chain is about 2 to 4 kilobytes. With MLDSA, each certificate carries a public key of roughly 1,312 to 2,192 bytes and a signature of roughly 2,420 to 4,195 bytes, depending on the parameter set. A single certificate could easily be 4 to 7 kilobytes. The full chain for a single TLS connection could grow from roughly 3 kilobytes to 12 to 20 kilobytes or more. Some proposals favor hybrid certificates that carry both a classical and a PQ signature during the transition, which further inflates sizes. On constrained clients, on IoT devices, on mobile networks with limited bandwidth and high per megabyte costs, that's a real problem. Flash and RAM constraints on embedded devices limit how much certificate data can be stored and passed. Lattice schemes code and key tables can be bigger than compact RSA or ECC implementations, which creates deployment challenges on devices with tight memory budgets. There is active research into lightweight lattice implementations tailored to embedded environments, but the trade-offs remain significant, and it compounds at scale. If you're a CDN or a cloud provider terminating billions of TLS handshakes per day, the aggregate bandwidth increase from larger keys and signatures is measured in terabits per second of additional traffic. That's not a rounding error, that's an infrastructure redesign. The research on lattice-based versus RSA performance shows that the trade-off is consistent across security levels. Lattice schemes generally have higher bandwidth and memory overhead, but comparable or better CPU performance than RSA at similar classical security levels, while also providing resistance against quantum attacks. For signatures and key exchange, current standardized lattice schemes use keys and ciphertexts or signatures measured in kilobytes rather than hundreds of bytes, yet often run faster than RSA on modern CPUs because they use structured linear operations that are amenable to optimization and parallelization. The important nuance is that the comparison point matters. Compared to X25559, which is the current standard for key exchange, MLChem is much larger and roughly comparable in CPU time. Compared to RSA 3072, which is the RSA equivalent at similar security levels, MLChem is larger in bandwidth but faster on the CPU, especially for server-side decapsulation where the RSA private key operation dominates latency. So the performance picture depends on what you're replacing and what you're comparing against. For organizations currently using RSA key transport rather than ECDH key exchange, the CPU improvement from migrating to MLChem is a genuine benefit. For organizations already using ECDH with X25519, the migration adds bandwidth cost without improving CPU performance. The security improvement, protection against quantum attacks, is the motivation in both cases, but the performance trade-off looks different depending on your starting point. For the Microsoft-centric enterprise, the impact lands on specific workloads you manage every day. Microsoft Teams media streams rely on TLS for signaling and media establishment. Every Teams call involves multiple TLS handshakes for the signaling channel, the media relay, and the authentication flow. SharePoint file access and OneDrive sync operations use TLS for every file transfer, and large organizations generate millions of these operations daily. Exchange Online Mail Flow uses TLS for message submission and retrieval, with StarTLS upgrades on connections that start unencrypted. Azure API calls from Power Automate connectors, Power Apps, and custom applications all use TLS handshakes that would need to accommodate larger messages. Entra ID token exchanges, which happen on every authentication and every token refresh, use TLS and carry signed tokens that would eventually use MLDSA signatures. And at higher security levels, the comparison shifts somewhat. RSA key sizes grow superlinearly with security level. To match AES 256 equivalent security, you'd need RSA with a 15/360-bit modulus or larger, which means keys over 1.9 kilobytes and dramatically slower exponentiations. Lattice parameters grow more moderately, so at very high security levels, the size gap between RSA and Lattice schemes actually narrows, and the CPU advantage of Lattice schemes becomes more pronounced. But most enterprise deployments operate at the AES 128 to AES 192 security level, where the bandwidth penalty is most acute. That's where your infrastructure is right now. One area that deserves special attention for this audience is the impact on Entra ID and Azure AD authentication flows. Every authentication to Microsoft 365 involves multiple TLS handshakes and token exchanges. When a user signs into Teams, the process includes a TLS connection to the login endpoint, a token request to Entra ID, a token response with a signed access token, and subsequent TLS connections to each service the token grants access to. At enterprise scale, millions of these authentication flows happen every day. Larger handshakes and larger token signatures compound across all of these flows, increasing both latency and bandwidth consumption on the authentication path that users experience directly. A 50 millisecond increase in authentication latency, which is plausible given the handshake size inflation, is perceptible to users and affects productivity at scale. For Power Platform specifically, the impact manifests through API call volume. A Power Automate flow that runs 10,000 times per day and makes 5 API calls per run generates 50,000 TLS handshakes per day for that single flow. An organization with hundreds of flows generates millions of API call TLS handshakes per day. Larger post-quantum handshakes increase the aggregate bandwidth consumed by these automated processes, and on network connections with limited capacity, this can introduce latency that affects the reliability of time-sensitive automations. So the performance reality is this: the new algorithms are fast enough on the CPU. The problem is everything else. Larger keys, larger signatures, larger handshakes, more bandwidth, more memory, more fragmentation risk, more middle box failures. And you can't just flip a switch to deploy them because the TLS ecosystem, the PKI, the certificate authorities, the browsers, the operating systems, the load balancers, the HSMs, all of them need to coordinate on the transition. And that's why you can't just swap algorithms. Which brings us to the real problem. It's not the math, it's not even the bandwidth, it's that your infrastructure is rigid. And everything we've discussed so far, the harvest now threat, the new lattice algorithms, the bandwidth inflation, all of it points to the same structural flaw. Your encryption is hard-coded, your certificates are hard-coded, your key types are hard-coded, and when the algorithm needs to change, the change can't propagate fast enough to matter. There's a way to bridge from where you are to where you need to be, but it requires a fundamentally different architecture for how cryptography works in your systems. The hidden dependency problem. Your enterprise has cryptographic dependencies you don't know about. Not some of them, most of them. And that's the problem that makes the post-quantum transition fundamentally different from a patch deployment or a certificate renewal. You can't fix what you can't see. and most organizations have remarkably poor visibility into where and how cryptography is actually used across their infrastructure. Think about what's running in your environment right now. You've got Federation servers authenticating users to Microsoft 365, using certificates for token signing and SAML assertions. Active Directory certificate services issuing certificates for domain controllers for VPN authentication, for document signing, for 802.1x network access, each of these use cases with different key types, expiration policies, and renewal workflows. Azure AD connects syncing identities between on-premises Active Directory and Entra ID using TLS connections and potentially encrypted credential stores. Custom Power Automate connectors calling external APIs over TLS, where the TLS configuration lives in the connector definition and may not be auditable through your standard security tooling. Self-signed certificates on internal web applications that nobody's updated in 3 years because there's no certificate management process that covers internal-only services. Hard-coded API keys in application configuration files stored in source control alongside the code with no rotation mechanism. Certificates baked into IoT firmware that can't be updated in the field because the device manufacturer never implemented a certificate renewal path. SSH keys on administrative jump boxes with no rotation policy because the operations team set them up 5 years ago and nobody's touched them since. And that's just what you know about. The ones you don't know about are the ones that will break the transition. Cryptographic dependencies buried in CI/CD pipelines, in build scripts, in deployment automation. Code signing certificates used in build processes that run on schedule and would fail silently if the signing key expired or the algorithm was deprecated. Certificates embedded in container images that get rebuilt from cached layers so the certificate version in production doesn't match what's in the repository. TLS configurations in legacy on-premises applications that were set up by someone who left the company 5 years ago with no documentation and no change management record. VPN concentrators with hard-coded cipher suites that can't be upgraded without a hardware refresh because the vendor no longer supports the firmware. Third-party SaaS integrations that terminate TLS on their side where you have no visibility into which algorithms they use or whether they've started supporting PQC. Database connection strings with hard-coded TLS parameters in application config files that span hundreds of microservices. Kuppinger Cole, an analyst firm focused on identity and security, characterizes crypto agility as a missing operational discipline. Organizations have pockets of capability but lack end-to-end governance and operationalization. And the reason is simple. Without continuous discovery, crypto agility is a slogan. You can't be agile if you don't know where the crypto is. That's why the Cryptographic Bill of Materials, or CBOM, is becoming a regulatory expectation rather than a nice-to-have. NIST's CSWP 39, published in December 2025, explicitly frames crypto agility as part of broader risk management and cybersecurity governance and emphasizes CBOMs as a tool for inventories and vendor risk management. The EU's ENISA guidance includes similar expectations, and the regulatory trend across multiple jurisdictions is moving toward requiring cryptographic inventories as part of standard security governance. The practical challenge with inventory is that it's not a one-time exercise. Cryptographic dependencies change every time a new application is deployed, a certificate is renewed, a library is updated, or a configuration is modified. A point-in-time inventory becomes stale within weeks. That's why the emphasis across all the guidance is on continuous discovery, not static documentation. Continuous discovery means running scanning tools on a regular cadence, integrating cryptographic findings into your configuration management database, and flagging any changes that introduce new or deprecated algorithm usage. A CBOM is essentially a software bill of materials but focused specifically on cryptographic components. It tracks which algorithms are used, where they're implemented, which libraries provide them, what key sizes are in play, whether those implementations are configurable or hard-coded, and what the supply chain looks like for each component. When an algorithm gets deprecated, whether that's because of quantum risk or a classical cryptanalytic breakthrough, the CBOM tells you exactly where the remediation work needs to happen. Without it, you're doing the equivalent of vulnerability scanning without an asset inventory. You're guessing at the scope of the problem. And this connects directly back to the Issaka inequality we talked about in the first section. X plus Y greater than Z. You can't estimate Y, the migration time, if you don't know the scope of what needs to be migrated. You can't prioritize which assets to protect first if you can't see which ones use vulnerable algorithms. The inventory isn't just a governance checkbox. It's the mathematical prerequisite for rational decision-making. For Microsoft-centric enterprises, the hidden dependency problem has a specific shape that's worth detailing. Your M365 environment is managed, so the TLS termination points and certificate chains on Microsoft's side are largely Microsoft's responsibility. But your hybrid infrastructure isn't. Your on-premises Active Directory, which still holds the primary identity store for many organizations and uses Kerberos encryption, that depends on specific algorithm suites. Your ADFS servers, which sign SAML tokens for federation to M365 and other cloud services, with token signing certificates that may be RSA-based and not easily rotated. Your custom applications calling M365 APIs using the Microsoft Graph SDK, where the TLS configuration may be buried in the SDK's default settings and may not be overridable without code changes. Your network equipment terminating VPN tunnels that connect remote offices to your Azure virtual network, where the VPN firmware may not support ML-Chem cipher suites. Your third-party SaaS integrations, where the authentication and data exchange paths may use cryptography that you've never audited. Your Power BI dashboards connecting to on-premises data gateways, where the gateway certificate may be self-signed with no rotation policy. Your Azure DevOps pipelines that sign build artifacts using code signing certificates stored in Azure Key Vault, where the key type determines whether the signed artifact can use a post-quantum algorithm. All of these contain cryptographic dependencies that you own and that you need to discover before you can plan the transition. And the discovery process itself requires specific tooling and methodology. Network-level scanning can identify TLS cipher suites, certificate chains, and protocol versions across your external and internal endpoints. Certificate management platforms can inventory every certificate across your PKI, flagging expiration dates, key types, and issuing CAs. Application security testing tools can identify hard-coded cryptographic parameters in source code and configuration files. But these tools need to work together because no single tool covers all three dimensions: the network layer, the certificate layer, and the code layer. The CBOM is the integration point that connects the findings from all of these sources into a single view of your cryptographic posture. One pattern that works well for Microsoft-centric organizations is to start the inventory at the edges and work inward. Begin with your internet-facing endpoints, because those are the most exposed and typically the easiest to scan. Then move to your internal network segments using passive monitoring of TLS negotiations to identify cipher suites and certificate chains without disrupting traffic. Then tackle the application layer using source code scanning and configuration auditing to find hard-coded cryptographic parameters. This outside-in approach gives you the highest impact findings first, while building the methodology for the harder inner layers. So you can't fix what you can't see. And even if you could see everything, your infrastructure probably isn't built to change, which is exactly what cryptographic agility is designed to fix. The agility architecture. And that's the real problem. Not the quantum computer, not the bandwidth overhead, the rigidity. Your infrastructure is hard-coded to use specific algorithms. Applications specify RSA or ECC directly in their configuration. Libraries pin specific cipher suites. Certificates are issued with specific key types and can't be reissued without manual intervention. HSMs are programmed with specific algorithm support that requires firmware updates to change. And the entire PKI, from root certificates down to leaf certificates, is built on the assumption that the algorithms in use today will remain in use for the lifetime of the certificate chain. When NIST standardizes a new algorithm or when an existing algorithm gets deprecated, every one of those hard-coded dependencies needs to be updated. And in most enterprises, that update process is manual, slow, error-prone, and runs across organizational boundaries that don't coordinate well. Cryptographic agility is the structural fix for this problem, and it's not a one-time migration to post-quantum algorithms, it's a permanent operational discipline. NIST's CSWP 39 defines crypto agility as the organizational, architectural, and operational capability to discover, replace, and evolve cryptography across complex systems without destabilizing critical services. Kuppinger-Cole defines it as the ability to replace or adapt cryptographic infrastructure without disrupting operations or security, treating crypto as a modular, manageable system property rather than hardwired code. Both definitions converge on the same point. Crypto agility means you can change the cryptography without breaking the system, and that capability has to persist after the quantum transition is complete, because there will be another algorithm deprecation, another cryptanalytic result, another compliance mandate. The question isn't whether your cryptography will need to change again. The question is whether your infrastructure can handle it when it does. So how do you build that capability? There are 4 architectural pillars. The first is modularity. Algorithms must be separated from application logic. Instead of an application implementing RSA directly in its codebase, it calls a cryptographic library, a sidecar, or a gateway that provides the encryption service. The application asks for a secure channel or a signed token, and the crypto layer decides which algorithm to use based on policy. When the algorithm needs to change, you update the library or the policy, not the application. Think about how this works in practice. Today, an application that needs to make a TLS connection might directly configure the cipher suite, the key type, and the signature algorithm in its code or configuration. If RSA is deprecated, you have to find and update every application that specifies RSA across your entire code base. In a modular architecture, the application calls a TLS library and says, "Give me a secure connection." The library's configuration, managed centrally through enterprise policy, determines which cipher suite and key type to use. When the policy changes from RSA to ML-KEM, you update the library configuration once, and every application that uses the library picks up the change. The second is abstraction via APIs. Applications request cryptographic services through well-defined interfaces that hide algorithm details. An internal API for key exchange returns a shared secret without the caller knowing whether it was established using X25519, ML-KEM, or a hybrid of both. An internal API for signing accepts a message and returns a signature without the caller specifying whether MLDSA or RSA was used. The algorithm choice is a policy decision, not a code-level decision. This is the same pattern that's already used in well-architected identity systems. When your application calls Entra ID to get an access token, it doesn't specify which signing algorithm should be used. Entra ID decides, based on its own policy. Your application just validates the token signature using the public key from the OpenID Connect Discovery endpoint. The OpenID Connect Discovery endpoint, which publishes the signing keys used by the identity provider, already supports key rotation through the JUX-URI endpoint. This is the same mechanism that would enable a transparent transition from RSA to MLDSA signatures on identity tokens as long as the token validation libraries support the new algorithm identifiers. The same abstraction applies to every cryptographic operation in your infrastructure. The third is policy and mechanism separation. The algorithms, key sizes, and cipher suites are defined in configuration files, management consoles, or policy engines, not in application code. When NIST publishes a new standard, you update the policy, and the crypto layer picks up the change. When a vulnerability is discovered in a specific implementation, you rotate to an alternative implementation of the same algorithm without touching the application. In a Microsoft-centric environment, this maps to familiar patterns. Azure API management policies can control which TLS cipher suites are accepted. Entra ID conditional access policies can enforce authentication requirements without changing application code. Azure Key Vault access policies determine which key types and operations are permitted. These are all examples of policy and mechanism separation applied to security decisions. The same principle needs to be extended to cryptographic algorithm selection at every layer. The fourth is hybrid mechanisms. During the transition period, you combine classical and post-quantum algorithms so that security holds if either one remains secure. This is the bridge from the current state to the post-quantum state, and it's the approach that's already being deployed in production. The specific hybrid mechanism that matters most right now is called X25519 MLKEM768. It combines a classical X25519 key agreement with an MLKEM768 key encapsulation. Both contribute to the shared secret through a key derivation function. If X25599 is broken by a quantum computer, MLKEM768 still protects the session. If a future cryptanalytic result breaks MLKEM, X25519 still protects the session against classical attacks. You don't need to trust one algorithm entirely. You get defense in depth at the key exchange layer. And this hybrid approach is already live in the ecosystem. OpenSSL 3.5 added support for ML-KEM and changed default TLS group preferences to include hybrid PQC-KEM groups, meaning that any server running OpenSSL 3.5 or later can negotiate hybrid key exchange without custom configuration. Microsoft Edge removed the post-quantum key agreement-enabled policy starting with Edge 147 because post-quantum key agreement became enabled by default and could no longer be disabled. Chrome has the same hybrid key exchange default. Firefox supports PQC through configuration flags. Cloudflare and Akamai have deployed PQC TLS support across their CDN edges, which means that a large portion of internet traffic is already being protected by hybrid key exchange, whether the origin servers know it or not. But hybrid isn't the end state, it's the on-ramp. Full post-quantum cryptography comes when the ecosystem is ready, when certificate authorities can issue MLDSA certificates, when HSMs can generate and store ML-KEM keys, when every client and server in your infrastructure can negotiate a post-quantum cipher suite without fallback. Agility means you can move from hybrid to pure post-quantum without rebuilding the architecture. The policy changes, the libraries update, the infrastructure keeps running. And the practical reality of hybrid key exchange is worth understanding because it's not without cost. Hybrid TLS handshakes are larger than either pure classical or pure PQC handshakes because they carry both the X25519 and the ML-KEM components. The client hello message with a hybrid key share is larger than a client hello with only X25519, though smaller than a client hello with only ML-KEM plus a classical fallback. The server response carries both the X25519 share and the ML-KEM ciphertext. The total handshake communication is larger than either pure approach, but you get the security benefit of both. The additional handshake size has been observed to cause issues with older middle boxes and some TLS inspection appliances, as we discussed in the performance section. But the trade-off is favorable for most organizations. Slightly larger handshakes in exchange for immediate protection against harvest, now decrypt later, for the negotiated session. The data in transit today is protected even though the data that was captured yesterday isn't, and that's the structural shift that matters. The current model is static. You pick an algorithm, you hard-code it, and you hope it lasts. The agile model is adaptable. You define a policy, the crypto layer executes it, and when the policy changes, the crypto layer adapts without breaking the applications above it. This is the same structural shift that other parts of enterprise security have already gone through. Identity used to be managed locally on each server with local accounts and local password policies. Then it moved to centralized directories like Active Directory, where policy was defined once and propagated everywhere. When the password policy changed, you didn't update every server individually, you updated the group policy and every server picked up the change. The same centralization needs to happen for cryptographic algorithm selection. And there's an organizational dimension to this architectural shift that's easy to miss. Modularity, abstraction, and policy separation require coordination between the teams that build applications, the teams that manage infrastructure, and the teams that set security policy. In most organizations, these teams don't have a natural coordination point for cryptographic decisions. Application teams specify algorithms in their code. Infrastructure teams configure TLS on load balancers and proxies. Security teams set compliance requirements, but nobody connects the three. The result is a patchwork of cryptographic implementations that nobody can change without breaking something. The agility architecture creates that coordination point. The crypto layer, whether it's a library, a sidecar, or a gateway, becomes the single place where policy meets implementation. Security teams define the policy. Infrastructure teams manage the crypto layer. Application teams call the API. And when the algorithm needs to change, the change happens at the policy layer, propagates through the crypto layer, and reaches the application layer without requiring any code changes. The broader PQC migration program across industry consistently follows a phased approach. Phase 1 is hybrid key exchange for confidentiality in live network protocols. This is where you get immediate protection for data in transit without waiting for every endpoint and certificate chain to be upgraded. Phase 2 is migration of certificates, signatures, and PKI to post-quantum or composite approaches. This is the harder part because PKI changes affect issuance, validation, revocation, device enrollment, and trust distribution across many systems. Phase 3 is full retirement of legacy RSA and ECC, where ecosystem support allows it. This sequencing appears across major migration frameworks because signatures and certificates tend to be more operationally complex than key exchange, especially in enterprise PKI, device identity, and trust anchor management. One reason Phase 2 is harder than Phase 1 is that certificate infrastructure has a longer dependency chain than key exchange. When you upgrade a TLS termination point to support hybrid key exchange, you're changing the configuration of a single component. When you migrate your PKI to MLDSA, you're changing the trust anchor for every system that relies on certificates issued by that PKI. You need to update the root CA key, reissue intermediate CA certificates, reissue end entity certificates, update trust stores on every client device, update revocation checking mechanisms, and validate that every application in the chain can handle the larger certificate sizes and different signature algorithms. This is a multi-year program even in a well-managed environment, and it's why the phased approach starts with key exchange and defers the PKI work until the ecosystem is more mature. The PKI migration also requires coordination with external certificate authorities, whose timelines may not align with yours. If your internal CA supports MLDSA but your external CA doesn't, you face a split PKI where internal certificates are post-quantum and external certificates are still classical. Managing that split state adds operational complexity until the external CAs catch up. Another reason is that certificate validity periods create a lag. If you issue a 3-year certificate today using RSA, that certificate will still be in circulation in 2029, even if you start deploying MLDSA certificates next year. The coexistence period, where RSA and MLDSA certificates are both in use, requires hybrid certificate chains or dual signing approaches, both of which add complexity and size to the certificate infrastructure. The deployment pattern that enterprises are following right now is consistent. Start with internet-facing TLS termination points, CDN edges, load balancers, ingress controllers, API gateways, because these are the most exposed to passive traffic collection and the easiest to update since they're typically under centralized control. Then move to operational access channels like SSH and VPN, which protect privileged administration and long-lived sessions. Then tackle PKI and signatures, which are the most operationally complex but also the highest payoff for identity protection. And there's a pattern that's worth highlighting for this audience. In many cases, the first phase of PQC deployment, hybrid TLS, is already happening without the enterprise doing anything. When a user connects to Microsoft 365 through a browser that supports x25519 MLK-M768 and Azure's TLS infrastructure supports the same hybrid group, the connection automatically uses post-quantum key exchange. The enterprise didn't configure this. The browser and the cloud service coordinated on the upgrade. This is the standards-led, vendor default rollout approach, and it means that a portion portion of your infrastructure is already post-quantum ready without any action on your part, but that doesn't mean you can skip the architecture work. The vendor default rollout covers the paths where both ends are modern and cloud managed. It doesn't cover the paths where one end is on-premises, or where the TLS configuration is managed locally, or where a middle box strips the PQC cipher suite. And it definitely doesn't cover the certificate and signature migration that comes in phase 2. For that, you need the architectural agility to change algorithms in your own infrastructure, and that requires the modularity, abstraction, and policy separation we've been talking about. The practical question for most organizations is where to start, and the answer is the same as the deployment pattern. Start where the exposure is highest and the control is tightest. External TLS termination points first, then SSH and VPN, then PKI and signatures, and at each step, build the architectural patterns that make the next step easier. Modularity in phase 1 makes phase 2 faster. Abstraction in phase 2 makes phase 3 manageable. Policy separation throughout makes every phase configurable rather than requiring code changes. Now, architecture is only part of the equation. The keys themselves need to evolve too. HSMs and key management for the quantum era. Hardware security modules have been the trust anchors of enterprise cryptography for years. They store private keys, perform cryptographic operations in tamper-resistant hardware, and provide the root of trust for certificate issuance and code signing. And for the post-quantum transition, they need to change fundamentally. The current generation of HSMs was designed around RSA and ECC. The firmware supports specific key types and algorithm operations, and adding support for MLChem or MLDSA requires firmware updates or hardware replacements. This matters because HSMs are deployed at the root of trust, and upgrading them touches every system that depends on that root. If your code-signing HSM doesn't support MLDSA, you can't sign software updates with a post-quantum algorithm, and every downstream system that verifies those signatures is stuck on RSA or ECC until the HSM is updated. The industry is responding, and HSMs are evolving from static vaults to what some vendors call crypto-agile trust anchors, devices that support hybrid key exchanges, multiple algorithm families, and firmware-updatable algorithm support. This evolution matters because the alternative is replacing your entire HSM fleet every time NIST standardizes a new algorithm, which is neither practical nor sustainable, given that NIST has already signaled it will continue developing additional PQC standards beyond the initial 4. The crypto-agile HSM model means that when NIST finalizes FNDSA or standardizes additional algorithms, you can add support through firmware updates rather than hardware procurement cycles. The key management implications of post-quantum cryptography go beyond just supporting new key types. MLChem and MLDSA keys require higher entropy than their classical counterparts at equivalent security levels, and the key generation process needs to account for that. The larger key and signature sizes mean that HSMs need more storage capacity per key object, and the operations that process these larger objects need more memory and bandwidth within the HSM boundary. Existing RSA and ECC hardware accelerators can't be reused for lattice operations, requiring new hardware designs and standards. For Microsoft-centric enterprises, the practical path runs through Azure Key Vault and Azure Managed HSM. The current PQC support status includes MLChem and MLDSA key types in preview, with key rotation automation for both. The key rotation capability matters more than most organizations realize because post-quantum key management demands shorter-lived keys and more frequent rotation than the current RSA and ECC practice of multi-year certificate lifetimes. The reason is structural. Classical keys like RSA 2048 can be used for years without significant risk of compromise through cryptanalysis, because the best-known attacks still require astronomical amounts of compute. Post-quantum algorithms are newer with less cryptanalytic history, and the risk of a future breakthrough that reduces their security margin is non-trivial. Shorter key lifetimes mean that if a vulnerability is discovered, the exposure window is smaller. Automated rotation through Azure Key Vault means that key replacement doesn't require manual intervention, and the application using the key doesn't need to be reconfigured. The operational principle is straightforward. Decouple key lifetime from certificate lifetime so that a key rotation doesn't require a full certificate reissuance and a certificate renewal doesn't require a key rotation. Automate rotation so that key replacement doesn't require manual intervention, reducing the risk of human error and ensuring that rotation happens on schedule even when the responsible person is unavailable. And ensure that the key management infrastructure can support algorithm changes without requiring a full reissuance of every certificate in the chain, which means designing your PKI so that changing a key type in Key Vault doesn't cascade into a rebuild of every certificate that depends on that key. Azure Key Vault's managed key generation handles the entropy requirements for MLChem and MLDSA automatically, but organizations running their own HSMs need to verify that their entropy sources and key generation procedures meet the requirements for post-quantum key pairs. The NIST standards specify minimum entropy thresholds, and some older HSM models may not meet them without firmware updates. So the architecture is modular and the keys are agile, but who decides what gets changed and when? And there's a deeper point about HSMs and key management that ties back to the governance theme. When you rotate a key in Azure Key Vault, there should be a policy that triggers the rotation, a process that validates the new key works across all dependent systems, and a rollback plan in case it doesn't. The key rotation itself is automated, but the governance around it, the decision to rotate, the validation of the result, and the accountability for any failures, that's organizational discipline, not technology. The HSM or Key Vault provides the mechanism. The governance playbook provides the decision-making structure. Both are necessary. The Microsoft stack right now, this is where the conversation shifts from theory to practice, because for this audience, the transition will largely be mediated through what Microsoft actually ships. And in 2026, there's more available than most people realize. Let's start with what's already live and generally available. Microsoft announced general availability of post-quantum cryptography APIs on Windows and .NET in late 2025. The SimCrypt cryptographic library, which underpins Windows and Azure's crypto operations, now supports MLKM and MLDSA. Developers can build quantum-safe applications on the Microsoft stack today using the same APIs they already use for cryptographic operations. The SimCrypt implementation passed NIST validation, and it's available in Windows 11, Windows Server 2025, and the .NET 9 runtime. This means that any application running on a current Windows platform can invoke MLKM for key exchange or MLDSA for signing without installing additional libraries or SDKs. And in May 2026, Microsoft Active Directory Certificate Services added MLDSA support. This is a significant milestone because ADCS is the backbone of enterprise PKI in Windows environments. Organizations can now issue post-quantum certificates from their on-premises PKI without waiting for third-party certificate authorities to support MLDSA. The certificate templates support MLDSA key pairs, and the enrollment process works through the same ADCS workflows that administrators already use. This means you can start deploying MLDSA certificates for internal use cases like document signing, code signing, and 802.1x network authentication without any dependency on external CA timelines. The ADCS MLDSA support includes enrollment via certificate auto-enrollment, certificate enrollment web services, and the standard MMC certificate templates interface. CRL partitioning, which was added in late 2025, helps manage the larger CRL sizes that result from MLDSA certificates. This is particularly important because MLDSA certificates are larger than RSA certificates, which means the certificate revocation lists that aggregate them are also larger. And CRL partitioning allows ADCS to serve partitioned CRLs that reduce the download size for clients checking revocation status. On the browser side, the news is even more concrete. Microsoft Edge removed the post-quantum key agreement enabled policy in Edge 147 because post-quantum key exchange became enabled by default. Chrome has the same default. When you connect to a website that supports X25519MLKEM768, your browser automatically negotiates a hybrid key exchange that includes post-quantum protection. You didn't configure anything. You didn't enable a setting. It just happens. Firefox supports PQC key exchange through configuration flags, with default support expected in an upcoming release. And that means something important for the Harvest Now Decrypt Later threat we discussed at the beginning. When you access Microsoft 365 through a modern browser, your TLS session already uses hybrid key exchange if the server supports it. Azure's TLS infrastructure has been deploying PQC support across its services. Cloudflare and Akamai, which front a large portion of the internet's TLS termination, have PQC support enabled by default. So a significant portion of your encrypted traffic to SaaS platforms, CDNs, and cloud services is already protected by post-quantum key exchange. Most organizations are already partially protected against Harvest Now Decrypt Later, and they don't know it. That's the payoff I promised in the first section. But, and this is critical, this protection is partial and asymmetric. It covers browser-to-cloud traffic where both sides support hybrid key exchange. It leaves out your on-premises server-to-server communications, your VPN tunnels where the concentrator may not support PQC cipher suites, your SSH sessions with RSA or ECDSA host keys, your internal PKI still issuing RSA or ECC certificates, and your custom applications running on older TLS clients that can't handle MLKM. And any traffic traversing middle boxes or legacy network equipment that strips unknown cipher suites loses the protection entirely. So the infrastructure is moving, but it's moving unevenly, and the gaps are exactly where your most sensitive operations live. Let me be specific about what you can do right now in 2026 with the tools that are already available. First, verify your PQC coverage. Check which browsers your users are running. If they're on Edge 147 or later, or Chrome 124 or later, they're already using hybrid key exchange for connections to servers that support it. Check your Azure services. Azure has been rolling out PQC TLS support across its services, and you can verify whether your specific Azure endpoints support X25519MLKEM768 by checking the negotiated cipher suite in your TLS connections. Second, build your CBOM. You don't need a sophisticated tool to start. Begin with a spreadsheet that lists every certificate in your environment, where it's used, what key type it uses, who issued it, when it expires, and whether the underlying system supports algorithm change. Include your on-premises ADCS certificates, your Azure Key Vault keys, your VPN certificates, your code signing certificates, your internal web application certificates, and your third-party SaaS integration certificates. This inventory is the foundation for every subsequent decision. Third, start testing PQC in non-production environments. With SimCrypt supporting MLChem and MLDSA on Windows 11 and Windows Server 2025, you can set up a test environment that uses post-quantum algorithms for TLS and certificate enrollment. Use the ADCS MLDSA support to issue test certificates. Use Azure Key Vault's MLChem and MLDSA key types in preview to test PQC key management. Run canary tests on low-risk internal services to measure the performance impact and identify any middle box or compatibility issues before you expand. Fourth, upgrade your TLS libraries and runtimes to versions that support MLChem and hybrid groups. If you're running OpenSSL 3.5 or later on your servers, they can negotiate hybrid key exchange. If you're running older versions, you need to plan the upgrade. If you have custom applications that use their own TLS implementations, verify that those implementations support PQC cipher suites or can be updated to do so. Fifth, establish your PQC migration plan covering M365, aligned with the government timelines that apply to your organization. If you're in the US and handle national security data, align to CNSA 2.0. If you're in the EU, align to the ENISA roadmap. If you're in Canada, align to the April 2026 planning deadline. If you operate across jurisdictions, map against the most aggressive timeline and use that as your baseline. For what's in preview or coming soon, the roadmap looks like this. Entra ID is working on PQC for identity tokens, federation protocols, and conditional access. When this lands, it changes the game for authentication to Microsoft 365, because the tokens that grant access to your entire collaboration suite would be protected by post-quantum signatures. That's a big deal for the Harvest Now Decrypt Later threat, because identity tokens are one of the highest value interception targets. Azure Key Vault has MLChem and MLDSA key types in preview, which means you can start testing PQC key management in non-production environments. M365 workloads like SharePoint, Exchange, and Teams will follow Azure's infrastructure, so PQC rollout for these services depends on the Azure TLS and key management layers being ready. The 2026 to 2029 roadmap, synthesized from Microsoft's public commitments and the government timelines that pressure them, looks like this. In 2026, the focus is planning, inventory, and enabling hybrid TLS on critical paths where you control both ends. You should be building your CBOM, identifying every RSA and ECC dependency in your hybrid infrastructure, and designating test tenants for early PQC features. In 2027 to 2028, active early adoption begins with hybrid TLS production pilots and PQC certificate enrollment for high-value internal services. By 2029 to 2035, default PQC across all Microsoft services, with deprecation of classical-only paths for any data with long-term confidentiality requirements. The government timelines create external pressure that shapes Microsoft's priorities. CNSA 2.0 targets 2026 for networking equipment, which means regulated customers will demand PQC-capable VPN and network products from Microsoft and its partners. The EU expects initial transition roadmaps by end of 2026 and high-risk systems by 2030, which means European enterprises using M365 will need PQC options in the 2027 to 2028 timeframe. Canada requires departmental plans starting April 2026, which means government agencies using Azure will be asking Microsoft for PQC readiness documentation. These deadlines are not aspirational, they come with compliance requirements, and regulated customers will demand PQC capabilities from their vendors accordingly. The message from regulators is consistent across jurisdictions. Start now, plan carefully, prioritize high-value data, and build the capability to change algorithms as standards evolve. That last point, the capability to change, is what cryptographic agility provides. Without it, you're running a race against a deadline you can't predict, with tools you can't update fast enough. With it, you're running a control program that can adapt as the threat environment evolves. So the tooling is moving, but tooling without governance is just technology waiting to be misconfigured. The governance playbook. And this is where most post-quantum transitions stall. Not because the algorithms aren't ready, not because the infrastructure can't handle it, but because nobody's decided who owns the decision, how to prioritize the work, and how to keep track of it over the years it takes to complete. This is the unglamorous part of the transition. No new algorithms, no performance benchmarks, no vendor announcements, just governance, which is the least exciting and most essential piece of the entire puzzle. Cryptographic agility isn't a technical capability you can buy. It's an organizational discipline you have to build. And that requires a governance structure that treats cryptography as a strategic asset rather than an implementation detail. Most organizations still treat cryptography as a low-level implementation detail instead of a strategic asset that requires governance. Technical controls like libraries, HSMs, and TLS configurations alone are not enough. True cryptographic agility is a systemic capability spanning architecture, supply chain, and governance. Enterprises now need formal enterprise cryptography programs to govern strategy, inventory, agility, lifecycle management, and vendor risk. The first element is executive sponsorship and a steering structure. Enterprise cryptography needs a CISO level or higher sponsor who owns it as a strategic risk domain. It needs an enterprise cryptography steering committee with representation from security, architecture, engineering, DevOps, compliance, legal, procurement, and key business units. The committee's mandate is to approve crypto standards, set roadmaps including PQC, and authorize major migrations. Without this structure, crypto decisions fragment across teams that don't talk to each other, and the inventory stays incomplete because nobody's accountable for completing it. The committee should establish an enterprise cryptographic standards document that defines approved algorithms, key strengths, and PQC strategies. It should set crypto agility requirements for new systems, mandating that new applications must support algorithm configurability, central policy control, and logging. And it should create an exception process for legacy or constrained systems, with compensating controls and time-bound remediation plans. The steering committee should also own the roadmap, deciding which systems get migrated in which phase based on the risk prioritization model and the available engineering capacity. This is not a decision that can be delegated to individual application teams, because each team will prioritize their own systems rather than the organization's highest risk exposures. The second element is continuous cryptographic inventory, not a one-time spreadsheet. Continuous discovery using network-level scanning of protocols, cipher suites, certificates, and algorithms across internal and external endpoints, machine-to-machine traffic, and APIs. The inventory must tie each cryptographic instance to the application, business process, and data sensitivity it protects, so you can differentiate high-risk usage in payment systems and regulated environments from low-impact test infrastructure. It must validate discovered crypto against current and post-quantum standards, flagging deprecated protocols, weak ciphers, and misconfigurations. And it should integrate CBOMs for key products and services to track embedded algorithms, libraries, and PQC readiness. Crypto inventory is widely described across industry guidance as the foundation of crypto agility. Without it, you're operating blind. The third element is risk-based prioritization. Raw inventory data isn't actionable. You need a scoring model that combines severity, meaning algorithm strength, and protocol age, exposure, meaning internet-facing versus internal, and business criticality. That scoring produces prioritized remediation queues with documented rationale that you can explain to auditors and board members. It should integrate with your enterprise risk taxonomy so that crypto risks are expressed in business terms like confidentiality risk to regulated data due to deprecated cipher rather than technical terms that only the security team understands. The fourth element is vendor and supply chain governance. Your agility is bounded by your supply chain's agility. Third-party products, cloud services, and embedded components hide cryptographic usage that you can't see or change. Your governance needs vendor evaluation criteria that include PQC readiness and roadmap, contractual requirements for timely support of deprecations and security updates, and lifecycle oversight that tracks crypto-relevant end-of-support dates and plans migrations proactively. Cryptographic posture should become a standard dimension in vendor risk assessments, alongside financial stability, data handling practices, and incident response capability. The fifth element is an operational continuous loop. Crypto agility should run as a continuous cycle, not a project that pauses between assessments. The loop is discovery, then validation against current policy and external standards, then application mapping, then risk prioritization, then remediation through existing ITSM and DevOps workflows, then reporting that aggregates metrics and trends for executives and boards. This loop aligns crypto operations with standard ITSM and SecOps processes, avoiding a separate silo. And there's a compliance deadline that reinforces all of this. FIPS 142 sunsets in September 2026. Organizations working on PQC migration must also address the FEPS 142 to 143 transition. The dual compliance pressure, migrating to post-quantum algorithms and upgrading validated modules, makes cryptographic agility not just a strategic advantage, but a practical necessity. Without agility, you're running two separate massive compliance projects simultaneously instead of one coordinated program. NIST's CSWP 39, published in December 2025, explicitly positions crypto agility as a governance requirement rather than a technical nice-to-have. The document provides structured technical levers, modularity, API abstraction, policy and mechanism separation, hybrid mechanisms, and a strategic plan for enterprise governance. It's the closest thing to an official blueprint for building this capability. The metrics that matter for tracking progress include inventory coverage percentage across your systems and endpoints, the percentage of crypto implementations compliant with current standards, the time from vulnerability or deprecation announcement to full remediation, the percentage of critical systems meeting crypto agility design standards, and vendor PQC readiness coverage, meaning the proportion of critical vendors with published PQC roadmaps. Reports should be tailored to their audience, risk posture and trend lines for executives and boards, detailed queues and SLAs for operations and engineering, and evidence of process and outcomes for audit and compliance. And the maturity model matters. Don't treat the post-quantum migration as a project with an end date. Treat crypto agility as a permanent operational discipline. The PQC migration is the first real test of that discipline. If you pass it by building genuine agility, you'll handle the next algorithm deprecation, the next cryptanalytic result, and the next compliance mandate without starting from scratch. Cupping a Cole characterizes the maturity gap this way. Many enterprises have pockets of crypto capability, typically centered around certificate management and HSM operations, but lack the end-to-end governance and operationalization that makes agility a property of the organization rather than a skill of specific individuals. The Cryptography Maturity Action Plan, or CMAP, is one framework for assessing governance readiness, inventory visibility, operational processes, and migration preparedness. It provides a structured way to evaluate where your organization stands and what needs to be built next. The important thing is not which maturity model you use. The important thing is that you assess where you are honestly and that you build the capability in the right order. Governance first, then inventory, then risk prioritization, then remediation, then continuous monitoring. Starting with remediation before you have governance and inventory is like performing surgery before you've diagnosed the patient. You might fix something, but you're just as likely to make things worse. Securing the communication backbone. And the final piece of this picture is the protocol layer. The foundational protocols that hold the internet together, TLS VPN protocols like IPsec and WireGuard SSH, and the certificate infrastructure that underpins all of them, are all in the process of being upgraded for post-quantum security. TLS 1.3 is the primary focus, and for good reason. It's the protocol that protects the vast majority of internet traffic, including every connection to Microsoft 365 Azure and every SaaS platform your organization uses. The IETF's hybrid design work for TLS 1.3 and NIST's migration guidance both support phased migration, and they emphasize that hybrid approaches are meant to reduce risk during transition rather than replace all cryptography at once. The production path in 2026 is hybrid TLS 1.3 with groups like X25519 MLKEM768, not a wholesale move to a new TLS version. The collaborative effort across the industry is substantial. Cloudflare and Akamai have deployed PQC TLS at their CDN edges, which means that traffic passing through their networks is already being upgraded to hybrid key exchange, where both sides support it. Google accelerated its migration timeline in April 2026, signaling urgency from one of the largest operators of internet infrastructure. Microsoft's Azure TLS infrastructure is rolling out hybrid key exchange across its services, following a phased approach that starts with the highest traffic endpoints. OpenSSL 3.5 has made MLKEM support available in the most widely used TLS library on the internet, which means that any server running a current OpenSSL version can negotiate PQC key exchange. And browsers have enabled hybrid key exchange by default, which means the client side of the ecosystem is already there. For VPNs, the impact of post-quantum signatures on handshake performance is significant and worth understanding in detail. Most enterprise VPNs use IKEv2 with IPsec, and the IKE handshake involves both key exchange and authentication through digital signatures. MLDSA signatures are several times larger than RSA or ECDSS signatures at equivalent security levels, which inflates the IKE handshake message. On site-to-site VPNs with stable, high-bandwidth connections, the overhead is manageable because the handshake happens once and the tunnel stays up for hours or days. On remote access VPNs over high latency or lossy networks, the larger handshake can meaningfully increase connection setup time, which affects the user experience for remote workers connecting to the corporate network. Some VPN vendors are already shipping hybrid key exchange support using the same X25519 MLKEM68 pattern that browsers and CDNs use. The signature side is harder because VPN certificates are typically issued by an internal CA that may not yet support MLDSA. The phased approach for VPNs, consistent with the broader migration pattern, is to upgrade key exchange first for immediate confidentiality protection, then migrate certificates and signatures in a later phase. SSH is a similar story. The key exchange can be upgraded to hybrid ML-Chem groups, but the host key verification step, where the server presents its public key for the client to authenticate, will eventually need MLDSA signatures. Larger host keys and signatures mean changes to the SSH protocol, to the known hosts files that clients maintain, and to the SSH agent forwarding mechanisms that administrators use for jump box authentication. OpenSSH has experimental ML-Chem key exchange support, and the SSH protocol is being extended to accommodate larger key and signature sizes, but the deployment timeline depends on SSH client and server implementations being updated across the infrastructure. For organizations that rely on SSH jump box architectures, where administrators connect through a series of intermediate servers to reach production systems, the signature size increase compounds at each hop. Each SSH connection in the chain requires a separate key exchange and host key verification. With MLDSA host keys, each hop carries larger signatures, and the total connection setup time for a multi-hop SSH chain increases proportionally. This is a manageable problem for interactive use, but for automated operations that open thousands of SSH connections per hour, the latency increase can be significant. The cross-border dimension adds regulatory complexity that global enterprises must navigate carefully. The CNSA 2.0 timeline in the US applies to national security systems and the contractors that support them. The ENISA roadmap in the EU applies to all member states and the organizations operating within them. Canada's departmental plans apply to federal agencies and their service providers. The UK NCSC's phased approach applies to government and critical national infrastructure. Australia's ASD mandates apply to specific categories of systems. A multinational corporation operating in multiple jurisdictions faces different timelines for different categories of systems, and the compliance requirements overlap rather than align. A practical approach is to map your infrastructure against the most aggressive applicable timeline and use that as your planning baseline. If you operate in the US and handle national security data, CNSA 2.0's 2035 deadline is your outer bound. If you operate in the EU and handle critical infrastructure, ENISA's 2030 deadline for high-risk systems is more aggressive. If you operate across multiple jurisdictions, the earliest applicable deadline drives your planning. The specific timelines from the major regulatory bodies are worth knowing precisely. CNSA 2.0 specifies that by 2025, web browsers and cloud services must support CNSA 2.0 algorithms, and new software and firmware must be signed with quantum-resistant signatures. By 2026, traditional networking equipment, including VPNs and routers, must use CNSA 2.0 algorithms. By 2030, traditional asymmetric cryptography must not be used for national security purposes. By 2035, the transition must be complete. The ENISA roadmap requires initial transition roadmaps from member states by end of 2026, high-risk use cases implemented by end of 2030, and full transition by end of 2035. Canada's roadmap requires initial departmental migration plans by April 2026, annual progress reports, high-risk systems complete by end of 2031, and all systems by 2035. These dates aren't suggestions, they're compliance requirements for the organizations that fall under their jurisdiction. But the long-term resilience model is what matters most. Cryptographic agility isn't just about the quantum transition. It's about being able to respond to the next algorithm deprecation, the next cryptanalytic breakthrough, the next compliance mandate, without starting from scratch every time. The quantum transition is the forcing function that exposes the rigidity in your infrastructure. Fix the rigidity, and you fix the problem for every future transition as well. Think about it this way. SHA-1 was deprecated in 2017, and organizations are still cleaning up SHA-1 dependencies in 2026. TLS 1.0 and 1.1 were deprecated in 2021, and legacy systems still running those protocols are still being discovered in enterprise networks. The migration to post-quantum cryptography is the same type of transition, but the stakes are existential rather than inconvenient. If you build agility now, the PQC migration becomes the first test of a permanent capability rather than a one-time crisis. That's the through line. Cryptographic agility is the difference between surviving the quantum transition and being broken by it. Not because agility is a magic technology, because agility is the structural property that makes every transition survivable. And that structural property, once built, doesn't just protect you from the quantum threat, it protects you from every future algorithm deprecation, every future cryptanalytic result, and every future compliance mandate. The transition exposes the rigidity. The agility removes it. Cryptographic agility is what separates organizations that will navigate the quantum transition from those that will be broken by it. The algorithms are standardized. The tools are shipping. The browsers are enabling PQC by default. The question is no longer whether the technology will be ready. The question is whether your infrastructure can adapt when the algorithm needs to change. Build the agility. Everything else follows. If this changed how you think about your security architecture, follow me, Mirko Peters, on LinkedIn. And if you want more of this, leave a review. It helps more people find it.